So we've looked at momentum as it applies to a single object. Now we're going to consider the momentum of a system of two or more objects. To do this, we're going to explore what happens with momentum during collisions and explosions. By the end of this lesson, we want to be able to compare and contrast the different types of collisions, predict how objects will behave in a collision when their masses or initial velocities are the same or when they're different. We want to be able to predict the direction of momentum for objects colliding in two dimensions and solve problems involving conservation of momentum. What we mean by conservation is we mean it's constant. Conserved means to be constant or not changing. All right, so here we go. So to begin, we're going to start by considering the momentum of these two billiard balls in this series of pictures. In these pictures, a stationary billiard ball, that's ball B, is set into motion by a collision with a moving billiard ball, ball A. Now, in this picture, we have to assume that both balls are on a smooth table, they both have the same mass, and that neither rotates before or after the collision. So, before the collision, the momentum of ball B is 0 because it's not in motion, it's stationary, while ball A has a momentum of 0.72 kilogram meters per second. During the collision, ball B gains momentum while ball A loses momentum. After the collision, ball A has a momentum of 0.018 kilogram meters per second, while ball B has a momentum of 0.702 kilogram meters per second. This shows us that the momentum that ball A loses, which is 0.702 kilogram meters per second, is exactly equal to the momentum that ball B gains. Now, when we take this momentum as a whole system, that is, we choose the system to be both the balls together, we see that the total momentum before the collision is this 0.72 kilogram meters per second, and after the collision, the total momentum is the same, the 0.018 of ball A plus the 0.702 of ball B is the same as the momentum prior to the collision. The momentum of each ball changes individually, but overall the total momentum of the two balls together remains the same. We say that the momentum is conserved, and this is called the law of conservation of momentum, which states, in the absence of an external force, the momentum of a system is unchanged. So in any system where all forces are internal, such as cars colliding or the atomic nuclei undergoing radioactive decay or stars exploding, the total net momentum of the system before and after that event is the same, and we say that the momentum is conserved. So collisions between objects occur all of the time. The law of conservation of momentum tells us that the momentum of the entire system of objects before a collision will be equal to the momentum of the entire system of objects after the collision. There's two types of collisions that we're going to look at. They're elastic collisions and inelastic collisions. Now, we have to keep in mind that regardless of what type of collision we're dealing with, the total momentum before a collision is going to equal the total momentum after the collision. So to define these two types of collisions, we're going to say that elastic collisions are collisions where objects collide and then bounce apart from each other. They move away from one another. And then in inelastic collisions, those are collisions where objects collide and stick together. We're going to look at each of them individually and talk about them. First, let's talk about elastic collisions. So, an elastic collision is one in which the two objects collide and bounce apart. Now, they may bounce apart along a one-dimensional line, or they may bounce apart in a two-dimensional manner. Either way, the total momentum before and the total momentum after are going to be the same. When it comes to problem solving, we'll deal with only one-dimensional elastic collisions, but we might see conceptual questions involving two-dimensional elastic collisions. Now, of these elastic collisions, we're going to kind of see two different types of elastic collisions. One type we're going to call the collide and stop type. The other type we'll call the collide and move away type. So let's talk first about the collide and stop type of elastic collisions. With these type of collisions, elastic collisions, we're going to start with one object at rest while the other object moves in and collides with the at rest object. When this happens, the first object comes in, collides with the second object, and the second object moves away while the first object stays put. So the whole collision would look something like this. The green object's at rest, red comes in, collides, that one moves away. Now in this type of collision, the momentum is conserved. If the two objects are of the same mass, when the red object comes in and collides, the green object is going to move away with the same velocity as the red object had. If the masses are different, say for example the mass of the red object is greater than the mass of the green object, then in that case, this object's going to come in and then it's going to, because momentum is conserved and momentum equals mass times velocity, because the green momentum is lower than the red momentum, it's got to move away with greater velocity if the red mass is greater than the green mass. Okay, because we have to conserve that momentum. However, if it's the opposite situation, if we have the green mass is greater than the red mass, then it's going to move away with lower velocity. So, because momentum is conserved, if the two objects have the same mass, the second object will move away with the same velocity as the first object. If the second object has a greater mass, it will move away with less velocity. If it has a smaller mass, it will move away with greater velocity. So that's the collide and stop type of elastic collision. Now let's talk about the collide and move away type of elastic collision. In this type of elastic collision, both objects are moving toward each other initially, collide, and then move away from one another. If they have the same mass and same initial velocity, they're going to bounce away from each other with the same velocity as they started with, just in opposite directions. If they have the same mass but different initial velocities, the velocities will trade places. So if the green one is coming in faster than the red one is, then those velocities will trade places as they bounce away from one another. The slower one will move away with the faster one's initial velocity and vice versa. However, if their masses are different, they will not trade velocities. When it comes to problem solving, we're going to have to pay attention to the direction of velocities and assign appropriate positive and negative directions. All right, so now let's talk about inelastic collisions. So in inelastic collisions, these are collisions where objects collide and stick together. So in this case, we might start with like the green mass at rest, the red mass comes in and they collide and then they move together with some common velocity. So a collision in which the two objects stick together and move with the same final velocity is called a perfectly inelastic collision, or sometimes a completely inelastic collision. So if I drop like a ball of clay on the floor and it sticks, it doesn't bounce or anything, or when two train cars couple together, that's an inelastic collision. The most common type of perfectly inelastic collision dealt with in problem solving is where one object like begins at rest and the second object collides with it, and then they moved away together with the same velocity. In such a collision, the initial velocity of the moving object is always greater than the final velocity of the combined objects, which makes sense, right? In order for momentum to be conserved, when the two masses become one mass, the velocity has to drop. So let's take a look at an example. Consider this situation where we've got a large fish that's swimming toward a smaller fish, and the smaller fish is at rest. If the larger fish has a mass of, say, 5 kilograms, and it's swimming with a velocity of, say, 1 meter per second, and it's going toward this smaller mass of 1 kilogram, we want to know what's the velocity of the larger fish immediately after lunch. Well, the net momentum before lunch has got to equal the net momentum after lunch. So what that means is the momentum, the total momentum of both fish before the collision has got to equal the total momentum of both fish after the collision. So the large fish which has this mass of 5 kilograms, is moving at 1 meter per second. The small fish with a mass of 1 kilogram is stationary. Then after the collision, both masses are together, moving with some common final velocity. So the momentum beforehand is going to be 5 kilogram meters per second, and the momentum afterward is still going to be 5 kilogram meters per second, but the mass has increased by 1 kilogram. So the final velocity has got to be lower than the initial velocity. And working this out, we see that that final velocity is 0.83 meters per second. Now let's suppose that this fish, this small fish, was not initially at rest in this situation, that instead it had another velocity swimming toward the large fish. We'll say instead then that this small fish was moving toward the large fish with, say, a velocity of 4 meters per second. In that case, the total momentum before is still going to equal the total momentum after, but let's see how that changes the final velocity of our big fish. So things are still the same here for our big fish. He has a momentum of 5 meters per second, 5 kilogram meters per second. But our small fish, here he's moving in the other direction, so we count his velocity as negative. He's moving in the negative direction, which means that our total momentum before the collision is just 1 kilogram meter per second. We still have an increase of mass to 6 kilograms. How does this affect then our final velocity? Well, we end up with, this time, a final velocity of our big fish of 0.17 meters per second. So the negative momentum of the smaller fish before lunch effectively slows the larger fish after lunch. If the smaller fish were swimming twice as fast, we would end up with a final velocity of negative 0.5 meters per second. And the significance of that would be that that final velocity is opposite to the initial velocity. So basically in that situation, if the smaller fish were swimming at twice the speed, so it's swimming at 8 meters per second, it's basically going to go into the large fish and cause the large fish to move backwards. Okay, so that's kind of one-dimensional collisions. Let's talk just briefly about a little bit more complicated collisions in 2 dimensions. So the total momentum of a system remains unchanged in any collision, regardless of the angle between the paths of the colliding objects. We can show the net momentum after a collision when different directions are involved by using the parallelogram rule of vector addition. In this figure here, we see a collision between 2 cars traveling at right angles to each other. Car A has a momentum directed due east, and car B's momentum is directed due north. If their individual momenta are equal in magnitude, then their combined momentum is in a northeasterly direction. This is the direction the couple cars will travel after collision. So momentum is also conserved in what is called explosions. By explosions, we mean when 2 objects are forced apart, such as this cannon here, or these 2 ice skaters pushing away from one another, or this firecracker exploding into 2 different pieces. So when an explosion takes place in one dimension, such as the cannon and the ice skaters, we have to pay attention to the direction of the velocity when calculating the momentum. One direction will be the positive direction, and one will be the negative direction. Whatever the nature of a collision, or however complicated it is, the total momentum before, during, and after remains unchanged. This is an extremely useful law. It enables us to learn a lot from collisions without knowing any details about the forces that act in the collision. We're going to see examples of these types of collisions and solve problems involving them in class. We'll see you then.